There is a battery sitting in a laboratory in Shenzhen right now that may be the most important object on Earth, not because of what it is, but because of what it means for your car, your country's economy, and a technology race that has quietly become the defining industrial competition of our time. You've probably heard that solid-state batteries are coming. You've probably heard that for years. And for years, they've remained just over the horizon, always promising, always delayed, always 5 years away from changing everything. But something shifted, and the shift didn't happen the way most people expected. It didn't happen in a Silicon Valley lab. It didn't come from a billion-dollar startup that promised to reinvent energy storage. It happened inside a government program most people in the West have barely heard of. It happened because China decided to stop treating this as a science problem and start treating it as an industrial war. And if that strategy is working, and there is growing evidence it might be, then the consequences for every automaker, every battery company, and every country that thought it could catch up later may be more severe than anyone is ready to admit. But before we get to what China built, we need to understand exactly why the world needed something new to begin with. For the last 3 decades, the story of electric vehicles has really been the story of one battery, the lithium-ion cell. It powered the first commercial EVs. It made Tesla possible. It made the $25,000 electric car conceivable. And it did all of that while getting cheaper and more capable every single year. At its peak, lithium-ion was one of the great manufacturing success stories of the modern era. But every technology eventually hits a wall, and lithium-ion began showing cracks a long time ago. The problem isn't that lithium-ion batteries are bad. They're remarkable. The problem is the gap between what they can do and what we actually need. They still require complex cooling systems to prevent overheating. They still lose meaningful capacity after a few thousand charge cycles. And no matter how many improvements engineers squeeze out of the chemistry, there's a fundamental limit to how much energy you can safely pack into a cell built around a liquid electrolyte. That liquid, the medium through which charged particles travel between electrodes, is flammable. It degrades over time. It places an upper ceiling on how much power can be stored in a given amount of space. And for years, that ceiling has been getting harder and harder to raise. Engineers began to suspect that the era of meaningful lithium-ion improvements might be drawing to a close. The gains were getting smaller, the costs were getting higher, and the performance gap between what customers wanted and what the chemistry could deliver kept stubbornly refusing to close, which led the entire industry toward the same conclusion. The next battery couldn't just be a better version of what already existed. It had to be built on completely different foundations. That's where solid-state batteries entered the story. And if you don't know exactly what makes them different, the explanation is simpler than you might expect, and the implications are far larger than most people realize. Inside every battery, charged particles called lithium ions move back and forth between 2 electrodes. That movement generates electricity. The medium those particles travel through is called the electrolyte. In every lithium-ion battery on the market today, in your phone, your laptop, your electric vehicle, that electrolyte is a liquid. Think of it as a highway that ions travel across every time you accelerate. It works. It has worked for decades. But that highway is also flammable, unstable at extreme temperatures, and physically limiting in terms of how much energy can move through it safely. A solid-state battery does something that sounds almost too simple. It replaces the liquid with a solid material. That single change rewrites almost every other constraint in the system. A solid electrolyte doesn't catch fire. It opens the door to new electrode materials, particularly lithium metal anodes, which battery scientists have dreamed about for decades because of how dramatically they can increase energy storage. It eliminates the need for heavy cooling systems. And it removes one of the primary mechanisms through which batteries degrade over time. The result, in theory, is a battery that stores roughly twice as much energy in the same physical space, charges dramatically faster, lasts longer, and is far less likely to catch fire. If all of that sounds almost too good to be true, that's because there has always been a catch. The science of solid-state batteries has been understood for years. The challenge was never the concept, it was making them real. Replacing a liquid electrolyte with a solid one turned out to be deceptively difficult, not in the lab, where controlled conditions made early prototypes possible, but in the factory, where you need to produce millions of identical cells day after day at a cost that makes commercial sense. And of all the different approaches researchers tried, the one that showed the most promise and the most manufacturing difficulty was a specific material class called sulfide electrolytes. Sulfide-based solid-state batteries offer the highest energy density ceiling of any approach being pursued today. Some research targets reach 450 to 900 watt-hours per kilogram. Current lithium-ion chemistry tops out around 200 to 300. That's not an incremental improvement, that's a generational leap. But sulfide electrolytes came with a uniquely brutal problem. They were catastrophically sensitive to moisture. During manufacturing, even microscopic traces of humidity in the air could contaminate the electrolyte material, degrade its performance, or ruin an entire production batch. This wasn't a minor inconvenience. It meant that anyone serious about manufacturing sulfide-based solid-state batteries at scale would have to reinvent how battery factories worked from the ground up. They would have to build ultra-dry production environments where humidity was reduced to almost nothing. They would have to design robotic assembly systems that minimized human contact with the materials. They would have to develop automated inspection systems capable of detecting defects invisible to the human eye. Most companies that encountered that manufacturing challenge did what companies tend to do. They kept the research going in the lab and promised that the factory problems would be solved when the time was right. China made a different decision. And that decision may prove to be the most consequential strategic choice in the history of the automotive industry. In January 2024, Beijing did something that had no real precedent. It gathered the fiercest competitors in the Chinese battery industry into the same room and told them to work together. The resulting organization was called the China All-Solid-State Battery Collaborative Innovation Platform, CASIP for short. What made it extraordinary wasn't just who was in the room, it was what it represented. CATL and BYD, two companies that had spent years competing for every single gigawatt hour of market share, suddenly found themselves in the same national program, sharing pre-competitive research, coordinating on manufacturing challenges, and operating under a unified timeline. 6 of the top 10 automotive battery manufacturers in the world were part of the alliance. The Ministry of Industry and Information Technology was involved. The Ministry of Science and Technology was involved. State-owned investment funds were committing capital. And within months, the Chinese government followed with an additional investment of over 6 billion yuan, roughly $830 million channeled directly into accelerating solid-state battery development among the country's leading manufacturers. One professor at Tsinghua University, speaking at the ceremony marking CASIP's formation, said something that captured the underlying anxiety driving the whole program. He warned that the industry needed to be prepared for the risk that solid-state batteries could overturn China's existing advantage in automotive batteries. That warning was striking not because it came from a pessimist, but because it came from one of China's most respected battery researchers, speaking to the country's battery elite. Even China's strongest players understood that this technology could reset the board entirely, and so China moved to make sure it wouldn't be caught on the wrong side of that reset. The structure of what followed was methodical in a way that competitors found difficult to match. Universities focused on electrolyte formulations. Chemical companies worked on producing pure sulfide compounds. Equipment manufacturers developed the specialized machinery needed to operate inside ultra-dry production environments. Battery companies optimized cell architecture. Automakers began designing vehicle platforms capable of accepting the new technology once it was ready. It was less like one company developing one product and more like an entire industrial nation aiming at a single target. But understanding a problem at the national level doesn't automatically make the engineering easier. And the engineering problems here were genuinely hard. One of the most stubborn challenges was the interface between the solid electrolyte and the battery's electrodes. Unlike a liquid, a solid material doesn't naturally flow across every microscopic surface inside the battery. Even tiny gaps create resistance. Resistance reduces efficiency, generates heat, and shortens battery life. Chinese research teams spent years developing new coating methods and higher pressure manufacturing techniques designed to improve contact between every layer of the cell. They experimented with more stable sulfide formulations that would maintain reliable performance across thousands of charge cycles. In battery manufacturing, a 1% improvement in production yield can save millions of dollars. A slightly more stable electrolyte can transform a laboratory curiosity into a commercially viable product. These aren't dramatic breakthroughs. They're the grinding, incremental, unglamorous work of turning physics into factories. By late 2024, CATL had entered trial production of 20 ampere-hour solid-state samples, a meaningful step from lab prototype toward pilot-scale manufacturing, targeting an energy density of 500 watt-hours per kilogram. Separately, researchers at the Chinese Academy of Sciences unveiled a prototype with an energy density of 451.5 watt-hours per kilogram and a claimed charging speed that raised serious eyebrows globally. By 2025, companies with solid-state battery teams exceeding 1,000 employees included CATL, BYD, Welian, Qingtao, and Sunwoda. Those aren't lab teams. Those are the early foundations of an industrial workforce. Both CATL and BYD set 2027 as the target for small batch production. BYD's planned solid-state cells would target 400 watt-hours per kilogram and be used in its ultra-premium Yangwang brand. CATL announced a pilot production program targeting 500 watt-hours per kilogram. Goshen High-Tech completed design work for a 2 gigawatt-hour all-solid-state production line, with a smaller pilot line already operating and vehicle testing underway. And China became the first country in the world to establish a formal technical standard, precisely defining what qualifies as a true all-solid-state battery, a regulatory move that positions Chinese industry to shape global definitions and international regulations before anyone else does. But here's what you need to understand, and this is the part that changes everything about how you interpret all of those announcements. The race is not about who builds the best battery in a laboratory. It never was. The race is about who learns how to build millions of identical batteries in a factory, consistently, cheaply, and without fail. Because the history of technology is littered with companies that had the best science and still lost everything to the competitor who cracked manufacturing first. Think about what happened with lithium-ion batteries themselves. Chinese companies didn't invent lithium-ion chemistry. That work happened in American, British, and Japanese research institutions. But Chinese manufacturers learned how to build lithium-ion batteries faster, cheaper, and at greater scale than anyone else on Earth. They built the supply chains. They built the factories. They trained the workforce. And over 2 decades, they turned a Western scientific achievement into a Chinese industrial monopoly. Today, the US sources roughly 70% of its battery imports from China, not because American companies couldn't do the science, but because they didn't build the factories. If the same pattern plays out with solid-state batteries and there is genuine reason to worry that it might, the consequences could be more severe. Because this time, the technology in question isn't just a component, it's the single most important part of the most important new vehicle category of the 21st century. And unlike other industries where technological advantages fade, manufacturing experience in advanced batteries compounds. Every year of production experience reduces costs, improves yield, expands the supply chain, and deepens the engineering knowledge embedded in the factory floor. Those advantages become harder to erase with every passing year. Now, does all of this mean China has already won? Not remotely. That's the part of this story that gets lost in the headlines. The real situation is more complicated and in some ways, more interesting. CATL's own CEO, Robin Zhang, acknowledged in a candid interview that mass commercialization of solid-state batteries by 2030 is unlikely and that initial applications will probably be limited to vehicles priced above 250,000 yuan. Even China's most sophisticated battery manufacturer is not pretending the finish line is close. Current solid-state prototypes cost between $220 and $300 per kilowatt-hour. Getting to mass market viability requires reaching below $100 per kilowatt-hour. Nobody, not in China, not anywhere, knows exactly how to bridge that gap yet. The remaining technical hurdles are not trivial. Sulfide electrolyte layers have been described by engineers as ceramic-like, dense, brittle, and unforgiving. Maintaining the constant high-pressure compression needed to keep solid layers in contact inside a battery cell creates design constraints that can eat into the weight advantage that high-energy density is supposed to provide. And lithium dendrites, microscopic metallic filaments that can form inside the battery during charging and cause catastrophic failures, remain a problem that even the most advanced research teams are still working to solve. And then there are the competitors. Toyota holds one of the largest solid-state battery patent portfolios on Earth and is targeting vehicle launches between 2027 and 2028. Samsung SDI aims to begin mass production of next-generation batteries for premium vehicles by 2027. Nissan has a 2028 target. Volkswagen-backed QuantumScape and Factorial Energy, working with Mercedes-Benz and Stellantis, are developing their own solid-state approaches with serious industrial backing. The United States invested $40.9 billion in battery and critical mineral manufacturing between mid-2023 and mid-2024. New gigafactories are rising. Government policy frameworks are being rewritten. The West has not surrendered. But here's the uncomfortable truth that sits beneath all of those announcements. Investment and intention are not the same as experience. China's battery industry has something that cannot be bought quickly or replicated by policy alone. It has a decade and a half of continuous, compounding manufacturing knowledge embedded in the most integrated battery production ecosystem ever assembled. That knowledge doesn't just live in company reports or patent filings. It lives in the thousands of process decisions made by engineers on factory floors, in the supplier relationships built over years, in the equipment calibrations that took countless failed batches to get right. And so the world now finds itself in a genuinely uncertain moment. The most transformative battery technology since the invention of lithium-ion is approaching commercialization. The competition to get there first involves not just companies but governments. Not just engineers, but economic superpowers. Not just automotive industries, but national strategies for who controls the future of energy, transportation, and perhaps much more. Here is what's at stake. Solid-state batteries could unlock electric vehicles with ranges approaching 1,000 kilometers on a single charge. They could make 10-minute charging genuinely feasible. They could be dramatically safer than anything on the road today. They could power the next generation of electric aircraft, advanced robotics, and grid-scale energy storage. Whoever builds those batteries at scale doesn't just gain market share in automotive, they gain leverage across multiple industries simultaneously. The country that wins this race doesn't just build better cars, it builds the infrastructure of the next economy. It controls the supply chains, it trains the engineers. It sets the standards. It earns the decades of manufacturing advantage that make it increasingly difficult for anyone else to compete on even terms. China is aware of this. That's why the country launched CASIP not as a corporate initiative, but as a national project, the way you'd mobilize for something you believe is genuinely civilization scale in its importance. The United States is aware of this. That's why battery manufacturing has become a strategic priority in Washington, in a way it never was a decade ago. Japan is aware of this. That's why Toyota has spent years building what it calls the world's largest solid-state patent portfolio, even as it's been late to the broader EV transition. The question that nobody can yet answer, and the question that will shape the global automotive industry for the next 50 years, is whether China's head start in manufacturing culture, supply chain integration, and national coordination can be overcome by the scientific talent, institutional depth, and capital markets of the rest of the world. The answer to that question won't be written in a laboratory, it will be written in factories, and the factories are only just being built. What happens next matters beyond any single product, any single company, or any single country.